Hey everybody! Today we're going to talk about propositions with multiple quantifiers. So we're going to try and see what a proposition looks like if we have a there exists and a for all statement in it. Just as an example, we're going to start without worrying about math. We're going to have x and y coming from the domain of people, and p of xy is going to be the proposition x and y are soulmates. Let's read this first one. So for all x means everyone. There exists someone such that they are soulmates. This one's kind of cute. You've probably heard some version of this before. For everyone, there's someone out there. It's a cute sentiment. All right. Versus the close but very different cousin. Just swap the order. There exists someone such that for everybody, they're going to be soulmates. So here are the words. So there is a person. We could potentially name this person. In fact, I will. Because why not? Say Pietro Boselli. And Pietro is everyone's soulmate. You should immediately see the problem with this. When I'm looking for a person may not be the same thing that everybody's looking for in a person. So this argument falls apart pretty quickly. Let's look at some math. So first one we've got is for all x, there is a y such that when we add them together, we're going to get 0. You're like, that means if this is true, no matter what x you hand me, I should be able to throw back a y. Okay, finding the y is pretty easy. There you go. So found the y. No matter what x you give me now, I can now tell you what y is going to be. So this is a true statement. Let's swap the order. So there is a y such that for all the x's, you get their sum is 0. That means the same y works for every x. That is what this is saying when we have the there exists first. You're like, really? I don't think so. And it's not true. Very easy to find a counterexample. All you have to do is pick two numbers that are different. So if x equals 1, then you would have y equals -1. This is the only choice for y. If x equals 2, then y is going to equal -2. And that is the only choice for y in that case. However, y equals -1 does not equal -2. So then the same y is not going to work for all of the x's. This is a false statement here in number B. Okay. It'll get confusing, but just have the very same approach. Read it in order. If you have there exists first, that means we're saying the same y is going to work for everybody. All right. So another thing that we talked about last time when we talked about quantifiers was we talked about negating the quantifiers. So here we go. It's very easy. It has pretty much no new rules. Just make sure that you're doing it in order. For instance, if we negate there exists y in R for all x in R such that x plus y equals 0. I probably shouldn't write that there. Now we just go through and we apply the negation to everybody in order. So just like last time, when we apply it to the there exists, it's going to flip. So now it says for all y. So for all y, there exists x. Beep, beep. Such that x plus y, or no, not x plus y equals 0. So I flipped, I kept the domain, flipped the quantifier, kept the domain, negated the statement. Kind of the same pattern that we had last time. And now to negate the statement, that would be the same thing as saying x plus y doesn't equal 0, like that. I like having my little such that's. It just helps me read these very condensed statements. So you can put the such that in there if you like. Okay. Basically what this says, interpretation-wise, you can always find a counterexample. So every y is going to have a counterexample. Example number 4. Now we have a lot of quantifiers on this one. Got a parenthesis over here that we shouldn't have. There we go. Okay. So we put the negation out here. We say for all x, there exists y. For all z, such that x plus y plus z is greater than 0 is going to be the same thing as there exists x. For all y, there exists z such that x plus y, or not x plus y plus z, greater than 0. Then we can negate that statement pretty easily using the power of less than or equal to. And remember, the equal to is important. And then just as a warning, do not change the order when you're negating things. Just like it's important when we were reading it at first, it's still important, so leave it alone. It's good. Okay. And that's really most of everything that I had today, but I want to bring us to an example that you will see in real analysis. I just want to play with this definition. So a real analysis definition for continuity of a function is if for every epsilon greater than 0, there is a delta greater than 0, such that for all x with x minus a less than delta, then we have f of x minus f of a is less than epsilon. There will come a time in your life when you're taking real analysis where if I come and wake you up in the middle of the night, I will expect you to be able to spit this definition out at me. Today is not that day. This is just, we want to play with it. I'm going to condense it down to our notation. So we've got right here, this is for all epsilon greater than 0. So there we go, for all epsilon greater than 0. There exists delta greater than 0. There he is. Such that for all x in R, comes in right here, we have that this statement implies this statement, which is all we have written right here. Okay, so this such that I put in here, again, just readability. It makes it easier for me to digest, and so I'm going to assume that it also helps you to digest it. And then I also got rid of this 0 right here in the definition because it's the absolute value. Of course it's bigger than 0. Okay. So then what we can do to make this even more succinct is we could like give this guy a name. Say he depends on the x and y, or x and delta, sorry, there is no y. And then this statement could depend on x and epsilon. There we go. So that's basically what we say right there. If we do this, then we can make our statement even shorter. So for all epsilon greater than 0, there exists delta greater than 0, such that for all x in R, P of x delta implies Q of x epsilon. Okay, this is continuity, but there are functions that are not always continuous. They're discontinuous, and so we need to know when that happens. So when discontinuity happens is when continuity is not happening. So if we negate this statement, we will have something that tells us when we have discontinuity. That's basically the purpose of doing this. Is I wanted another example to negate that will be helpful for you to have maybe been exposed to. So let's negate this. Okay. So we're going to distribute it to the for all first. That turns into a there exists. And then remember, it is very important to keep your domain the same. We do not do anything to this greater than 0. We keep our domain. Okay. And then next we have there exists delta, which is going to turn into a for all delta. Let's see. There exists epsilon for all delta. And then this is the next guy. So there exists x in R. Again, the domain stays the same. I'm going to keep my little such that. And then we have not. P of x implies Q of x. I don't think we've negated a conditional before. So that'll be exciting. Let's do that. In order to negate the conditional, what we want to do is we want to change it over to its OR definition. Remember, that was like theorem 1.2.2. I had you prove it on a worksheet. So this all stays the same. And then such that, let's see, so it's going to be not P or Q. It is the same thing as the conditional. It has the same truth value. They are equivalent. And now we can distribute that negative here on the outside using De Morgan's law. So that's going to be a P and not Q. So then if we try and take it back, all right, let's copy this down. I'm a sucker for writing everything down. Okay, let's sub in what we know about P and Q now. So there exists epsilon greater than 0 for all delta greater than 0 such that we can find an x such that x minus x minus a is less than delta, and f of x minus f of a is, let's see, the negation of q would mean, what was q? This is q, so the negation means we need a greater than equals to. There we go. Okay, we might not know what this means, but we can sure as heck negate it. Here you go, translating it back into the full definition, that at least that you would like see vernacularly show up in real analysis. We've got our there exists an epsilon for any delta such that there is a x satisfying our less than delta and also greater than or equal to epsilon. And then that's all I have. Again, don't worry about understanding this definition. Worry about, oh, I see where the for all there exists and that stuff come in. I see how this was a statement that implies this statement. I see how we manipulated all these tiny statements. I might not know what it means overall, but I do know how to manipulate this and negate it. That's what I'm looking for right now. Okay. That being said, that's all I've got for now, and I will see you next time.